Welcome to lessons 5.6 and 7. You'll notice that this particular PowerPoint is 51 slides long, but please stick with me because we are going to gloss over a lot of it because this is about derivations in terms of applying the kinetic molecular theory to the different gas laws. And since we've already been using the gas laws, we're probably not that interested in how they're derived. As we get to the end of the presentation, we'll look at some root mean squared velocities and how you calculate effusion and diffusion rates. And that's where the meat of this is. So please bear with me as we work through these slides. Kinetic molecular theory is used to explain why gases behave the way they do. And with the kinetic molecular theory, we assume that everything is an ideal gas. Real gases do not actually fit the theory. There have to be slight modifications in that, just like in physics, when you're doing free fall problems, you ignore air resistance, and same kind of thing here. We ignore that gases sometimes don't behave ideally. So this is our best explanation at this point without adding extra mathematical complications. So the parts of the kinetic molecular theory, one of the parts says that particles are so small compared with the distance between the particles that the volume of the individual particles themselves can be assumed to be zero. So when a gas occupies a container, like in the beach ball on the right, then when we talk about the volume of the beach ball, we talk about the volume of the beach ball basically being empty space, even though there are gas molecules in that volleyball, or in that beach ball, sorry. Particles are also in constant motion. That's another part of the kinetic molecular theory. The fact that they're in constant motion causes them to have collisions with the walls of the container, and that exerts pressure. The particles are assumed to exert no forces on each other. That means they neither attract nor repel one another, and that helps us with the volume calculations because there's no interaction between the gas molecules. They're very antisocial. And then this last postulate of the kinetic molecular theory gives us our definition for temperature. Kelvin temperature is scientifically defined as the average kinetic energy of a collection of gas particles. And so that's how we know where absolute zero is, because of the kinetic molecular theory. And so this is, as I mentioned, this is using the kinetic molecular theory to go through Boyle's law. And then we'll go through the other laws as well. And I'm just going to basically kind of skip through these. If you want to look at these and watch how they derive these relationships, please feel free to pick up the PowerPoint on the Canvas site and look through them yourself. So this is pressure and temperature. And then volume and temperature. This is Charles' law. Avogadro's law, they also use the kinetic molecular theory. And then Dalton's law as well. They use the kinetic molecular theory to rationalize and derive Dalton's law. Ideal gas law. And most of these variables you've seen before. The U squared with the line up over the top of it is probably a new one to you. That's the average of the square of the velocities. And then if you've taken a physics course, this is the average kinetic energy formula, or the kinetic energy formula, and with just a slight modification here where you would have a velocity squared. So they're continuing to work on deriving the ideal gas law. As I was talking about, the last postulate mentions the Kelvin temperature being the average kinetic energy of gas particles. And then we come to the root mean squared velocity. Notice they take the kinetic energy and kinetic energy formula, and they put in the U squared with the line over it to symbolize in place of the velocity squared. Another variable that's a little bit different than what you're used to seeing, and we're going to use this formula here in just a second. So you can figure out the root mean squared velocity of a gas particle by using this equation. 3 is a number they needed to make it equal. Otherwise, it was just proportional. Also, they needed to throw in this constant, R, to make it equal. Temperature will be measured in Kelvin. And how do I know temperature will be measured in Kelvin? Because in this particular constant, it is in Kelvin. And then this last one, this capital M indicates the mass of a mole of gas particles in kilograms. So normally you see mole abbreviated with a lowercase m, n, and this capital M means you need the mass of the mole of gas particles in kilograms. So we're going to work through calculating the root mean square velocity for the atoms in a sample of helium gas at 25 degrees Celsius. Notice there's only one number in this problem. But where are we going to go? We're trying to figure out the root mean square velocity. What do we know? We know the temperature. That was the one number given in the problem. We know our value for R. And then there are some other things that we're going to need. What is the mass of a mole of helium in kilograms? Well, periodic table tells you that helium is 4 AMUs. And so if we put that into kilograms, first we use the molar mass, grams per mole, and then we divide it by 1,000 and we get 4.00 times 10 to the negative 3 kilograms per mole. So you put all those numbers in, and I know it looks kind of messy with all the variables in there with it, but 3 times 8.3145 times 298, and then you divide that by 4 times 10 to the negative third, you end up with the square root of 1.86 times 10 to the 6 joules per kilogram. And then when we take the square root of that, and because we know that joules can be that particular unit, things cancel out and we end up with meters per second, which is a velocity unit, and so that works out okay. So when we have gases in a gas sample, we cannot tell you which direction the gas is going to go. The path of that gas particle is very erratic. And so usually gases cover very small distances before they collide with something, and they can look and they can find the molecular velocity depends upon how many gas particles you have in the container. Temperature is, if the higher the temperature, the fewer times that you're going to have collisions, because they're just moving so fast that they don't really come in contact with each other. And so this join in is talking about that. We're going to skip through that because, again, that's not mathematical. But let's look at this. Consider 3 1-liter flask at STP. So it's at the same temperature and pressure. All these flasks, same volume, same temperature, same pressure. Flask A contains helium gas, B contains oxygen gas, and C contains hydrogen gas. Which flask do they have the lowest average kinetic energy? Now recall, the average kinetic energy is based on temperature, and so that would indicate that all of these would have the same average, all of them would have the same average velocity or kinetic energy. Now sorry, my bad, do they have the highest average velocity? Let's go back and look at these. This is the one where they have the lowest average kinetic energy. This is the one where they're all the same. I do apologize. So this one is not correct. Which one do they have the highest average velocity? Well, if you recall, on the bottom of that formula, so there was some stuff up here, and on the bottom was the molar mass. And so if you look, since molar mass is on the bottom, you're looking for the one with the highest average velocity, not kinetic energy. The highest average velocity is going to be the one with the lowest molar mass. And so hydrogen gas is about 2, oxygen gas is about 32, and helium gas is about 4. So flask C, the one with the hydrogen gas in it, is actually going to be the correct choice here. Same kind of thing, 4 identical 1-liter flasks contain the gases helium, chlorine, methane, and ammonia, each at 0 degrees Celsius and 1 atmosphere pressure. So again, same volume, same temperature, same pressure. Which one do they have the highest velocity? Again, you're looking for the one with the lowest molar mass. So this is about 4, this is about 71, this is about 16, and that one's about 17. And so helium, those helium atoms are going to have the highest average velocity. The last part of this PowerPoint talks about diffusion and effusion. Diffusion is basically, you've known diffusion for a lot of years in your education. The rate of the mixing of gases, the rate of diffusion is the rate of the mixing of gases. Now, effusion is a little bit different. sometimes when we want to pass a gas through a tiny orifice into an evacuated chamber, they can do a lot of studies with this in terms of how they basically can characterize the gas based on its effusion rate. And so here is a diagram of what effusion looks like, or a picture of what effusion looks like. So we've got a gas over on the left-hand side. We have a tiny pinhole in the middle, and then the other side is a vacuum. So basically the vacuum part of this chamber is going to pull the gas over, but it has to pull it through that tiny pinhole. So if we have two gases on the left-hand side, what's the effusion rate going to be for the gases? And so when you look at effusion rates, it's going to be the molar mass. And I know that this is again given as an M, a capital M, but please note that you don't have to convert to kilograms because you're dividing them by each other. So just if you have grams over grams, it's the same as having kilograms over kilograms. So there's no need taking that extra step and turning it into kilograms. Please also note that this is square root, and if you want to know the rate of effusion for gas 1 to gas 2, then you actually flip it on the other side. So you're going to look at the molar mass of 2 over the molar mass of 1, and the square root of each of those. So we're going to calculate the ratio of the effusion rates of hydrogen gas and uranium hexafluoride. First off, we need the molar masses. Notice that uranium hexafluoride is much, much, much more massive than hydrogen gas. And what we just learned, that law that we looked at, that's called Graham's law. And so notice there's our hydrogen's going to be our gas 1, our uranium hexafluoride is going to be our gas 2. And we put them over here, put the molar masses in, go ahead and divide that out and take the square root, and we end up with 13.2. What that means is through that little pinhole, the hydrogen molecules are, the rate of those moving through that pinhole is 13 times that of the uranium hexafluoride molecules moving through there. So effusion rates are going to depend on the average velocities, and that effusion rate makes sense because if you look at the average velocity formula we just talked about, the smaller the molar mass, the more that molecule is moving around, the more chance it has to find that pinhole. And again, they used the kinetic molecular theory to derive that. And here, this is the last slide. This is an experiment I used to do when I taught high school. It's an interesting little experiment because it talks about diffusion rates. And so what you do is you take a cotton ball that has hydrochloric, it's basically dipped in hydrochloric acid. It doesn't have to be a very strong concentration of hydrochloric acid. And you have another cotton ball that you dip in ammonia. And then at the same time, you put them at the end of a glass tube. That is not a vacuumed out tube, it's just a tube with air in it. And those molecules will diffuse down the tube until they meet, and they'll form ammonium chloride where they meet. And this is kind of showing the path that these particular molecules might take as they move through the tube. Hydrogen chloride is going to be about 36.5. Ammonia is going to be about 17 grams per mole. And so you would expect the ammonia to move quicker, have a higher velocity than the hydrochloric acid because the ammonia has a much smaller molar mass. All right, that concludes this slideshow. This is the end of chapter 5, and so we will begin shortly working on the next chapter.